guys, welcome back to my channel. So today here I am with an interesting topic of the subject operating system. As you can see, it is assigned by my college. So let us see what is it. So as we can see our title, that is SJF scheduling. So first we'll see what is scheduling, then SJF scheduling. About this we'll see in our video. Let's proceed with it. See what is scheduling. The process scheduling actually is the activity of the process manager which will handle the removal of the running process from the CPU, and as well as it will select the another process on that particular strategy. And the process scheduling is an essential part of multi-programming operating system. Next we'll see our title definition. What is SJF scheduling? So SJF scheduling. First, what is the full form of SJF? SJF full form is shortest job next. It is also known as shortest job first, or we can also call it as shortest process next. So it is a non-primitive algorithm as well as it is a primitive algorithm too. So shortest remaining time is a primitive variant of SJN. So the shortest job first is a scheduling algorithm in which the process with the smallest execution time will be selected for the execution next. So it can be primitive or non-primitive. It also reduces the average waiting time for the other processes which are waiting for the execution. So let us see the next. So if we have taken a title or topic, surely it would be having an advantage too and disadvantage too. So let us look at the SJF advantages and disadvantages. What is the advantage of SJF is, as we have seen earlier, with the smallest execution time, the process will be selected for the execution next. It can be a primitive or non-primitive. So for the batch of long-term scheduling, so the burst time it can be estimated from this job description itself. So we need to predict the value for the next burst time. So it will be regard to have an average turnaround time. So let us see the disadvantage. Disadvantage is it is frequently used for long-term scheduling because it reduces the average time over the first in first out algorithm. So it will give the lowest average waiting time also. So we need to know for this the appropriate things for the jobs running in the batch which are known should be in advance. So here the job completion time must be known earlier, but it is hard to predict we don't know, we can't find something. So it is often used in the batch system for the long-term scheduling. So it can be implemented for CPU scheduling for the short term. So it can cause very long turnaround times or sometimes starvation. So let us see the types of SJF scheduling. There are two types, as you can see. One is primitive SJF and another one is non-primitive SJF. So in primitive SJF scheduling, first we will keep the jobs in the ready queue as they will come. So next the process which have the shortest burst time will start executing first, and the process with the shortest burst time will be arriving next. So the current process will remove and the next will be arriving by the shortest burst time. It will be allocated by the CPU cycle. Next we will see is non-primitive. In non-primitive scheduling, once the CPU cycle is allocated to the process, it will hold till it will reach to the waiting state or it is terminated. If we have selected a process, till it won't finish, we can't make it terminate. Let's see the problem. Consider the set of 5 processes whose arrival time and the burst time are given below. If the CPU scheduling policy is SJF non-primitive, calculate the average waiting time and as well as average turnaround time. So as you can see, there is a process time is given below, arrival time is given and the burst time is given. Let us create a Gantt chart with the help of this. So now we'll start with the process P1 as it has arrival time 0. So we'll allocate first P1 and we'll mention here 0. It will complete in the burst time of 4 milliseconds. So we'll mention here 4. Next we'll see according to the burst time, because as we have seen in SJF non-primitive definition, it will be according to the burst time. So after P1, the process which will be occurring at next is P3 because it has arrival time 1, which is the smallest of all the burst time. So we'll allocate P3 next. Next we'll add 1 to 4 to go to next process. Next we'll see is P4, because after the burst time 1, it is the burst time 2, which is the smallest after 1 in all this burst time. So we'll add this 2 to 5, we'll get the answer 7. Next, after P4, we'll allocate the process P2 because it is next to greater than P4. Next, we'll allocate the process P2 and we'll add 3 to 7. So we'll get as 10. Next, we'll allocate the process P5, which is at last, and we'll add that 6 to 10 and we'll get the answer 16. So we have seen how to make the Gantt chart. Now let us go and calculate the average waiting time and average turnaround time. So I have kept this as for reference. So let us see how to calculate waiting time and turnaround time. So the process P1, the waiting time is 0 minus 0, that is 0 milliseconds, because in P1 we have not started doing any process. We'll see that from the process P2, the waiting time is 7 milliseconds, and arrival time is 1 millisecond. So our waiting time is 6 milliseconds. Next we'll see for P3. P3's arrival time is 4 milliseconds, and the arrival time is 2 milliseconds. So 4 minus 2 is 2 milliseconds. Next we'll see for P4. P4 arrival time is 5 milliseconds and arrival time is 3 milliseconds. So 5 minus 3 is 2 milliseconds. Next for P5. P5 waiting time is 10 milliseconds and arrival time is 4 milliseconds. So 10 minus 4 is 6 milliseconds. What is the total waiting time is adding the waiting times from the process P1 to P5. So 0 plus 6 plus 2 plus 2 plus 6 is 16 milliseconds. Average waiting time will divide this by the process 5, because there are 5 processes, will divide it by 5. So 16 by 5 is 3.2 milliseconds. So the average waiting time for the particular Gantt process is 3.2 milliseconds. Next we'll see turnaround time. What is the turnaround time? For the process P1, the turnaround time is 4 because it's completed in 4 milliseconds. So 4 minus 0 is 4 milliseconds. Next we'll see for P2. P2 completion time is 10 milliseconds and it is arrival time is 1 millisecond. So 10 minus 1 is 9 milliseconds. Next we'll see for P3. P3's completion time is 5 milliseconds and the arrival time is 2 milliseconds. So 5 minus 2 is 3 milliseconds. So next we'll see for P4, the same process, the completion time is 7 milliseconds and arrival time is 3 milliseconds. So 7 minus 3 is 4 milliseconds. Next we'll see for P5, the completion time is 16 milliseconds and the arrival time is 4 milliseconds. So 16 minus 4 is 12 milliseconds. Let us calculate the total turnaround time, that is 4 plus 9 plus 3 plus 4 plus 12, that is equal to 32 milliseconds. And average turnaround time is 32 by total 5 processes. So 32 by 5 is equal to 6.4 milliseconds. So as we have finished seeing the problem of the SJF non-primitive scheduling, now let us see the SJF primitive scheduling problem. So consider a set of 6 processes whose arrival time and the burst time are given below. If the CPU scheduling policy is SJF primitive, calculate the average waiting time and average turnaround time. So the process time, arrival time and the burst time are given below, and the available time I have made it for teaching for the understanding of myself and for yourself too. So let us make a Gantt chart of it. So we'll take the process P1 as first because the arrival time is 0 millisecond. So we'll take it as 0 and next we'll add 1 to it because the difference in the criteria is 1 millisecond. So next we'll move to the process P2 and we'll add 1 to it. After adding 1, we'll see the P1 has a burst time of 7 milliseconds. So we'll keep P1 in the ready queue. After keeping P1 in the ready queue, we'll be having still 6 available, still 6 balance. So we'll move towards to next problem, that is P2. Next process. So next process P2, we'll add only 1 to it because of a criteria, that is 1 difference. So 1 to 2. So here also the burst time is 5 milliseconds and we have used only 1 millisecond. So still 4 are balanced. So we'll keep our available time as 4 milliseconds. Next we'll move to the process P3 and the P3 so still now also we'll take 1, we'll add 1 to it. So 2 plus 1 is 3 and we'll keep So P2 is also in the ready queue because still it is having the 4 milliseconds, and we'll keep P3 in ready queue because still P3 is having 2 milliseconds balance. So next we'll move to P4, that is 3 to 1, and the burst time of P4 is completed because it is only 1 millisecond. So as the one process is completed, we can move towards our before process, which is already in the ready queue. So if we'll compare P3, P2 and P1, we will see the lowest available time is of P3. So we'll take P3 again. So after taking, we'll take again 1 milliseconds, that is 4 to 5, and we still will see our available time is 1 millisecond. So again, if we compare P3, P2 and P1, we'll see the lowest time available is P3. So again, we'll execute the process P3. After adding 1 to it, we'll get the answer 6, and the available time for P3 will be 0. So P3 process is is also completed. So after completing the P3 process, let's move towards the process of between P5 and P6. So as you'll see, the burst time is lower for P6. It's only one is available. Burst time is available, so we'll go for P6 as we have done in SJF non-primitive. So when we have executed process P6, only one it is used, and there is no available time balance. So 6 to 7, 6 plus 1, 7, it will move towards 7. Next, after 1, we'll see P5, P2 and P1. In the lowest burst time is of P5, that is 2. So we'll allocate the P5 by next process. So already for us P3 process and P4 process are completed. So let us make me a mark. P3 process and P4 process is completed, and now P6 process is also completed. So now let us see is P5 process. P5 2 burst time we have included. So here 2 burst time is also completed. Here also available time is 0 milliseconds. So the P5 process is also completed. Now when we'll compare P2 and P1, the lowest burst time is of P2, that is 4. So next we'll move towards the P2. So 9 plus 4 is 13. We'll add P to it, and in our ready queue the process P2 is also completed. Next, the last process balance is P1. So the time available time is 6 milliseconds. So we'll add 13 plus 6, that is 19. And the last time of this process executing time, finishing time is 19 milliseconds. So in our ready queue, P1 is also finished. So our ready queue is empty, and all processes are also completed with the help of this. So let us go next. So now let's see how to calculate the waiting time and turnaround time. So the process P1, the finishing time is 19 milliseconds and the arrival time is 0 milliseconds. So the difference between them is 19 milliseconds. For the process P2, the finishing time is 13 milliseconds and the arrival time is 1 millisecond. So the answer is 12 milliseconds. For the process P3, the finishing time is 6 milliseconds and the arrival time is 2 milliseconds. So the difference between them is 4 milliseconds. Likewise for P4, the finishing time is 4 milliseconds and the arrival time is 3 milliseconds. So 4 minus 3 is equal to 1 millisecond. For the process P5, finishing time is 9 milliseconds and the arrival time is 4 milliseconds. So the difference between them is 5 milliseconds. For the process P6, the finishing time is 7 milliseconds and the arrival time is 5 milliseconds. The answer is 2 milliseconds. So as we have to calculate the total waiting time, we have to add all the processes waiting time. By adding all those, we'll get the 43 milliseconds. As we have to get the average, we have to divide the number of the addition of the all processes by the number of process. Number of processes is 6. So we'll divide it by 6. We'll get the answer as 7.1 milliseconds. Now let us calculate the turnaround time. For the process P1, the waiting time is 19 milliseconds, arrival time is 19 milliseconds and the burst time is 7 milliseconds. So 19 minus 7 is 12 milliseconds. And the turnaround time for the process P2, the arrival time, waiting time is 12 milliseconds and the burst time is 5 milliseconds. So 12 minus 5 is 7 milliseconds. And for the process P3, the waiting time is 4 milliseconds and the arrival time is 3 milliseconds. So 4 minus 3 is equal to 1 millisecond. For the process P4, the waiting time is 1 millisecond and the arrival time is 1 millisecond. So answer is 0. So it is 0 milliseconds. For the process P5, the waiting time is 5 milliseconds and the arrival time is the bus time is 2 milliseconds. So 5 minus 2, that is equal to 3 milliseconds. And for the process P6, the waiting time is 2 milliseconds and the bus time is 1 millisecond. So 2 minus 1, that is equal to 1 millisecond. What is the total turnaround time is by adding all those processes. By adding this, we'll get 24 milliseconds. And we have to calculate average turnaround time, that we have to divide by the number of processes, that is 6. So 24 by 6 is equal to 4 milliseconds. So that's all. Our SJF primitive scheduling and non-primitive scheduling is so easy to learn. So we have finished the SJF primitive scheduling, SJF non-primitive scheduling with their problems too. So thank you for your support and keep supporting, guys. Let's meet in next video. Bye.